This is Computer Programming 1 from the University of Washington. Welcome back. I'm Martin Dickey. Today we'll be talking about strings. Now, strings are something that are very, very useful in practical programming, but we don't need them in every program. As we go through today's lecture, we'll start with string constants, and actually character constants as well. We'll talk about the main concept of null-terminated array representation. This is the basic notion of strings as they are used in C. We'll spend quite a bit of time looking at some functions in the standard C string library and see a peek into string initializers and talk about how we might use arrays of strings as well. Character data is quite common in some types of programming. Names of things, of people, messages, labels, headings for things occur very often in certain types of programming. All of those ideas involve characters, usually multiple characters rather than single characters. Our ability to handle multiple characters in C so far is quite limited. What we have been able to do easily is have character constants or individual characters. These are shown with single quotes around them. They include special characters like the line feed \n, and as we'll use today, a special character called the null character. We've also used some string constants without making much of a fuss about them. We saw these in printfs, for example. We could use a printf to print a message like Bill is very rich, or we could use a format string like this one that includes placeholders. Both of these, you notice, are enclosed in double quotes, not in single quotes, and that is the chief punctuation difference. Internally, strings are stored in character arrays. Since we understand characters, they're fairly simple, and we understand arrays and how to process them, putting the two together into the idea of a string shouldn't be too much of a stretch. The catch is learning exactly what the functions are and observing some rules and conventions that programmers and that library functions are expecting when strings are used. The chief convention is that at the end of every string, the null character is stored. This character is symbolized in the program as a \0. Like a \n, it's not really two separate characters. It's just a symbol for one character stored in the machine occupying one character position. If we have a string sample, as we do here, we show that it's a string by putting it in double quotes. Internally, this will be stored as an array of characters, and the \0 or null character is inserted at the end. Making sure there's room for the \0 character is one of the tricks to getting string programming right. With string constants, the compiler takes care of inserting the \0 automatically. However, there are other cases where C is not quite so nice to us. The programmer has to be quite careful to be sure the \0 or null character is present wherever it's needed. One of the things the programmer must worry about is making sure there's enough room in the array. The null character does occupy one character position, beyond the data characters. Even an empty string with apparently no characters in it occupies a single character. That character contains the null. Notice that this punctuation difference translates into an internal difference in the computer. Both of these two expressions are legal in C, X with a single quote and X with a double quote. But they are different. X with a single quote occupies 1 byte of storage and contains just the value for the character X. X with a double quote is a string. Strings are terminated with a null character. So X with a double character occupies two positions in memory. The first one contains the X character, and the second one contains the null character. When programming with strings, the kind of operations you might find yourself needing are things like copying or assigning one string to another, comparing, finding the length of a string. This is often important in formatting printed material so that it is legible, clear, concatenating or combining strings, and doing I/O. Unfortunately, we can't do all of these things as directly as we would like to do. The underlying reason goes back to the fact that strings are arrays of characters. And we know that arrays have some limitations. So almost all the limitations of arrays will continue to be limitations for strings. For example, we can't compare one string with another, and we can't assign one string to another. We'd like to a lot of the time, but we can't do it directly because arrays don't allow this facility, and strings are arrays of characters. Fortunately, there are library functions already written which will help us to do these operations. In order to use them, though, we'll have to study them, learn what parameters they expect and what their operation is. Of course, another alternative is to write your own code and to write your own functions to handle strings. This is also possible now that you know what a string is in its underlying representation. But if the string library function exists, it's nice to take advantage of someone else's work and use that. The library that contains the string functions is called string.h. So if you plan to use those functions, you should put a $include string.h directive at the beginning of the program. All of these string functions will expect that your strings are properly terminated. That is, that they do have a null in the right place. This is how the library functions know how long your strings are. It is very rare to find a library function to which you pass a length parameter. Instead, the library functions will expect that there is a null character to terminate the string. Generally, these library functions will also produce a correctly null-terminated string. However, that's not always true, and it's one of the reasons why understanding the operation of individual functions is important. Let's look at several of these now. The first one I'd like to look at with you is called string length. This function returns the length of a string. What it does is count how many characters there are before the null character. It doesn't include the null character in the count. So the string A, double quotes, that makes it a string, has length 1. The null string, no characters, has length 0. Now, there may be a little bit of confusion between the length of the string and the size of the array. The length of the string A is 1. By definition, the length is the number of characters not counting the null. But the array that holds that string has to have size at least 2, because there will be a null character there, and there must be room for it in the array. So this is often a point of confusion when conversing with someone about strings. The size of the array versus the length of the string currently stored in the array. Here's one that's a little longer. If you counted the characters, I think you'd find that there were 22 in that string, null-terminated string. String length would return the value 22, which could then be stored in an integer variable k. String length is in the library, but if you don't remember what its name is, you can't use it. Or if for some reason you don't wish to include the string library, you could write your own string length function. That's also good practice in writing functions, in using arrays, and in using strings. So here's how we could implement our own string length function. The one in the library would look very similar to this. The function requires a string as its parameter. what is a string? Well, it's nothing more than an array of characters. So the correct parameter type would be char, and then a variable or parameter name followed by empty brackets. Remember that with one-dimensional arrays, empty brackets are allowed, as long as the function has some way of determining what the length of the array is. And it does, because of this convention or agreement that arrays will be terminated with a null character. The heart of this string length function is the loop, which adds 1 to a counter every time it finds another character. We'll initialize the counter to 0. Then the condition of the while loop, the reason that we'll continue in it is that we haven't come to the null character yet. S sub n not equal null character. As soon as we hit that character, we're finished. We can return n. If you think about it carefully, you'll see that n at that point has exactly the right value. We haven't counted the null character. And we'll return the value. Let's look at another frequently used library function, string copy. I can't assign one array to another, but I could write a loop to copy characters, or I could call this function that effectively does the same thing. It requires 2 arguments. One is the string we're copying from, and the other is the string we're copying to. When I go to use string copy, my main problem is remembering which is which. Does the destination come first or does it come second? If you're not sure, take a look in a reference book to find out, because getting them switched will give you the wrong answer for sure. One way to remember it is to imagine that there's a gets symbol between the two. Think of it as dest gets source, and you can remember which way the two go. The chief pitfall in using string assignment with string copy is making sure that dest is large enough to hold the result. The string copy function does not check this. It assumes dest is big enough. And if its assumption is wrong, disastrous things can happen. Let's look at the use of this function with an example. Here I've declared 3 character arrays. My intention is to use them to hold strings. I'll begin with a string copy that takes the string 7 and copies it into the variable named medium. When I'm done, medium will look as it does on the bottom of the screen. I'll have the message 7 plus our friend the null character at the end. Let's do a couple more copies. Let's copy from medium into big. Okay. Well, medium we just finished putting a value to, the 7. I copy it into big, which is quite a bit larger, 1,000 characters in size. We'll only copy up to the null character. The rest of the array big will remain uninitialized. Its values are unknown. But that's generally all right, because the values past the null character will be ignored by string library functions, and they probably should be by the functions and the code you write too. Let's do the next statement. String copy big, comma, Bob. Which direction are we copying? Think of it as big gets Bob, and you would be on the right track. Now, all that we copy is BOB and the null character. So the result is what you see below. BOB null character and then 7. Those values are still there. String copy does not go through and clear out or do anything with the part of the array after the null terminator. Now you might wonder, I have 2 null terminators in here. Which one is the real one? Well, the answer is that string processing is typically done left to right. So the functions that are using this variable as a string will be scanning left to right, looking for that first null, and they will ignore anything beyond it, even though there are other null characters in that array. You can get into trouble, though, if you don't have an array that is large enough to hold the result. Let's do another assignment. Copy medium to small. Okay. this example shows the result of copying the contents from big to small, actually, not what I said at first, medium. Big, you remember, is the one we just saw that has two nulls in it, first one after Bob and the second one after score and 7. So when I copy big to small, it's surprisingly harmless. I'm not copying 1,000 characters to 5 characters. I'm only copying as far as the first null character, and that fits perfectly well inside small. On the other hand, if I copy from medium to small, there is a problem, because medium doesn't have a null until you get to the end of the 4, score, and 7. The string copy function doesn't check the size of small. It simply copies characters until it reaches a null. The result, as you see it there, is an overflow. We've filled up small, and we have also stored characters outside small. What is that area we've stored into? The answer is we don't know. It's probably part of our program. It may be other variables sitting there, x or j or k or some other array. What we've just done is silently and without intending to clobber those variables. Now, this is certainly not a syntax error. The compiler doesn't know this is going to happen. What's more, the error that this produces may not be obvious at this point. It may only be later, when you use those clobbered variables, that something goes very wrong. And tracing it back to this programming error can be extremely difficult. The moral is, always be sure that the destination array is large enough to hold the data it's going to contain. How do you know how large it is? Well, you may remember that the size of the array is one thing, the length of the array is another thing. So in determining whether you have enough room in an array, you need to look at the length of what you're copying from and compare that to the size of what you're copying to. That gets a little tricky. But it has to be done, or terrible things like this can happen. As with string length, we could write our own. And this is often just for practice, as a way of getting familiar with the concepts. This function has as its core the while loop, where we take one character, source sub I, and assign it to another character, dest sub I. Now we have to worry about getting the loop condition right, initialization. And there is one piece of final processing that's very important. We want to make sure that the new destination array has that null character in it. If you look very carefully at the way the while loop is structured, the null character won't be copied to the output by the while loop itself. The check for the null character terminates the while loop before the copy is done. And so you have to do it as an independent step at the very end of the algorithm. Let's look at another string library function. This one, string concatenation, is used to append or concatenate one string. The idea here is that we will place one string directly after another so that the result is a single string rather than two of them. There will only be one null character in the result when we're finished. So if one string is lamb and the other is chop, then the result would be lamb chop. The syntax is similar to string copy. We have the source and destination, and you have to be sure you get them in the right order. Destination comes first. The way this works is that the string in destination is not changed, at least not up to its null character. Starting at that null character, we will start copying characters from the source. And when the source has been copied, its null character is placed in destination. So the new string will be longer than either of the original ones. It's very important, again, to be sure that dest is big enough, or disasters like the one we just saw can happen. Here's how this might look in the code. I do a string copy to get an initial value into str1. I do another string copy to initialize str2. str3 has been declared, but so far is uninitialized. Now I can copy string 1 into string 3. This is where I want the final concatenated result to be. That is done with a string copy. Finally, I can call my new concatenation function and concatenate string 2 into string 3. Now watch what happens as I do this. You'll notice that the first part of string 3 stays the same, but watch, it's the second part that changes and gets the copy from string 2. This is concatenation of strings. Another function is string comparison. It turns out to have a surprise in it, and we'll have to carefully consider what this surprise is so we don't make mistakes in our programming. The idea is to compare two strings. Now, it may be we just want to see if they're equal. But in many cases, we make decisions based on strings. We want to put names in alphabetical order, or within our phone book, we want to have the subject headings put in alphabetical order. And this involves comparing two strings, checking to see if pizza comes before or after physicians, for example. Our string comparison function will help us with these kinds of comparisons as well. Now, the peculiar thing about string compare is it returns an integer. It doesn't return a true false or a Boolean. Here is the details of this. String compare returns negative if S1 is less than S2. Now, by less than, we mean comes before. Equals means we'll return a 0. Positive value is given back if S1 is greater than S2, that is, comes after it in sequence. Now, exactly what does it mean to compare when things aren't equal? Well, what we'll do is compare letter by letter until we find a character that isn't equal in the two. At that point, we'll simply compare those two characters, and we can determine which one is in order by that. So if I'm comparing lamb and wolf, I can stop on the very first character. The L and the W are different, and the L comes before the W. So we're going to say that lamb is less than wolf. What about lamb and lamp? The first three characters are all the same. The fourth character, position 3, B versus P, the B comes first. And so we'll say that the whole word, the whole string lamb, is less than lamp. In the third case, all of the characters in the first one are in the second one. They're exactly the same. But then I have additional material beyond. So a couple ways to look at that. We could just say there's a rule that the shorter one comes first. Or we could say we're comparing the null character of lamb to the C of lamb chop. And it turns out the way the characters are arranged, the null character comes first. How do you know for sure what character comes first? This depends upon the sequence used by a particular computer. Most computers use the ASCII sequence, and in it, the letters and numbers are all in the expected order. But when comparing between categories like letters and numbers, it may not always be obvious what the order is. In that case, you can turn to a reference manual and see what the order of characters is for the ASCII sequence, or whatever sequence you may be using in your computer. It's quite important to remember that the result of the string compare is not a Boolean. It's not true and false. Remember that it's an integer. It could be positive, negative, or 0. There are 3 possibilities, not 2. If you're comparing two strings for equal, this is a particularly easy mistake to make. You can't say if string compare S1, S2 is true, print the same. You must compare them to 0, which of course in C we know is false as a Boolean. So this is rather a surprise. We cannot treat this as a Boolean. In many cases, you may set up a series of 3 comparisons with an if statement. 1 for equals, 1 for less, and 1 for greater than. There is one area where strings are a little nicer than arrays in general, and that is using strings for I/O with printf and scanf. Now you may remember that for arrays in general, I can't use printf and scanf. There isn't an array placeholder character. I have to break the array into its individual pieces inside a loop in order to printf or scanf. However, the scanf and printf functions, library functions, do recognize strings, and the placeholder for them is %s. Both scanf and printf understand the null character. Printf will be looking for it, and scanf will place it there if you type a string in from the keyboard when scanf is trying to process your request. So scanf will do the right thing, except it doesn't know the size of the array. And so you still have to be quite careful about this. In this example, I've shown scanf. It's been asked to read a string. The data is going into the character array buffer. Notice that there isn't an ampersand on buffer. That's not a mistake. That's because arrays are passed by reference. And since strings are arrays, this is the correct way to call scanf, to do input on a character array. Note that if we were doing input on a single character, this would not be right. We would need to provide a character variable there and make it a pointer by putting an ampersand in front of it. Another comment on this example is that scanf isn't checking the size of the array. So a malicious user would be able to type more than 2,000 characters, 2,001 or 3 or maybe 5,000. Scanf would happily place these extra characters into memory, and they would clobber whatever was there. This flaw in scanf has been used as a security attack in a number of hacking incidents over many years. This is just a sample of the string functions that are in string.h. For many of the functions we've looked at, there are additional forms which might have additional parameters. For example, for string cat, there's also a string ncat, which allows you to specify the maximum length of the strings. There are also functions for converting between various types and storing them into strings. There are others. An interesting project for tonight might be to take your favorite C book or reference manual, find the section in it that describes strings, look up a couple of the ones we've studied today and see how the description there matches what we presented here. Then you might leaf through and see what other string functions are there so that when you do string programming, you'll have an idea of what you can come back to help you write programs more easily. There's a related library I'd like to point out. It's called ctype.h. Stands for character type. This has a number of useful little functions that operate on single characters, things like converting a character from upper to lower case, or testing whether a character is a number or a digit. That's another library you might wish to be familiar with if you're going to be doing programming with characters and strings. The fact that these functions are in libraries emphasizes a point that I've made before in this course, that being able to use libraries and functions is a central skill to C programming. Many useful functions exist in the standard libraries that all C compilers have to comply with. And there are also many specific libraries for particular applications that are available, or in particular companies or work groups, there may be libraries that have been developed by colleagues over the years. You really won't be an effective programmer until you're completely comfortable with functions and comfortable with the idea of using functions already written in libraries. As a little bonus, let me go back to the idea of initializing a string. Here's one way we could do it, and this uses the array initializer notation that we discussed briefly in connection with arrays. If this isn't familiar, you could do it the old-fashioned way by initializing every single character individually. Is there an easier way? Well, there is a special way of initializing strings that's often extremely convenient. In the declaration of a character array, you can have an equal sign and then a string constant. Okay. Now, be careful about size, as always with strings. Lamb has only 4 visible characters in it. But as a string, the null character will be there. So if you declared pet to be size 4, you would have just made a mistake. Always be careful about size and length with strings. Here's something that we can't do in C. I sure wish we could, but it just doesn't work. I can't declare a variable and then later try to assign a string constant to it. Okay, really would be nice, but you can't do it. Array assignment doesn't exist in C, not even for strings. If you want to do something like this, the only chance you have is when you declare that variable. Initializers are not assignment statements. Most of the time you don't have to be aware of that, but here's perhaps the first case where there is a difference. Something you can do in an initializer that you can't do in an assignment statement that looks practically identical. Here's another little bonus topic. It's sometimes helpful to have arrays of strings. For example, in a program that was displaying calendars or dates, you might want to have ready access to all of the months of the year in string form. It's very convenient to define a single array, call it months, that contains these values as strings. Now, when we first introduced 2D arrays, I mentioned that there were 2 ways to view a 2D array. One is as a table of characters with 2 dimensions. But the other way is as a single array, a single dimensional array whose entries are the rows. And that's effectively what we've done here. I'm thinking of the array month as having size 12 rather than size 12 by 10. This way, by using only one subscript, I can pull out an entire row, which in this case is a string, and use it effectively. Look at the example we've given. We want to printf the name of month 7. Okay. Well, the reference month 7, that's a 2-dimensional array. So the 7 says everything in row 7. And that's precisely August, the string August. Let's wrap up what we've said by going over the main points we talked about today. Strings, by definitions, are null-terminated arrays of characters. They're not fully a type in C. They share many limitations with arrays. But there are some things that C or the library do for us. For example, scanf and printf recognize strings with the %s placeholder. To use strings effectively, the best policy is to master a few of the functions in the library, such as string copy, string length, string cat. There are others. If you scan the reference manual, get familiar with them, you'll know they're there when you need them. The major pitfall in a string is overrunning the available space, as well as somehow losing the null character. You won't use strings in every program, but you'll find them useful for those programs that handle strings and characters. Please join me next time as we continue with another topic in this course.